Hello, everyone. Very good morning. Uh, Thanks for having me over here. I'm delighted to be able to present this at the BIM Coordinator Summit. Thanks to the organizers of this event. Today, I will be talking on the weakest link in BIM and Precast. I am Shadaab Sayed. I am an engineer at Punch Consulting Engineers. A little about me. I have been working in precast design and coordination industry since the past 4 years. I have been mostly involved in design and coordination processes. I have a bachelor's in civil engineering from Pune University, and I've been working with Punch Consulting in the same domain. So, a little about Punch and what we do. Punch, we are one of Ireland's leading engineering consultancies. We have offices in cities and two five cities and two countries, and we have about 49 years plus of experience in consulting business. It's a 50th year that this year, and we have about 100 plus engineers, staff, technicians, and administrative staff, and we are a growing company. So I'll get to the topic. It's about precast and how BIM is useful in it. So just a little about precast. It is creating structures in a factory. I mean, like in small bits, and then assembling those on the site. So these units are sometimes very small. They come in varying sizes, and the thing is that you need to have these to be able to fit in the correct position. Like these units, like suppose there's a wall or a building. These will be created in small units, and then they'll be transported to the site, and they'll be required to be fitted in, just like assembled on the right location and at the right places. So it involves a lot of coordination so that you have your drawing and everything in the correct place. All the elements that you produce are of the correct size and stuff. So we need to have everything well coordinated, and it is very. And when you have BIM processes, when you have model based collaboration, clash checking, and all those things, it makes it very useful to avoid any clashes, avoid any kind of errors on site, so that the product that comes out from the factory is of good quality, and it gets easily assembled on site. So a little about the process that we have, and I mean, like, what output do we need. So basically, when we are creating models, we are basically generating data. So this data is kind of acting as an input to another machine. So the model that you create, like whatever, if it could be a building, it could be a bridge, it could be anything that is precast. So there are two ways of creating precast. It could be an automatic machine based on a carousel line, or it could be a bespoke formwork. So the way this works is, in most typical elements that we have, like solid walls, twin walls, or maybe flow plates or anything, it's most of our automated process. So whatever thing that we model in the in the model environment, be it Revit, Tekla, Plan Bar, or anything, uh, it generates a file in the backend, which is a PXML or Unitechnique data that is fed to the production system. So the model basically generates data, and then that data is supplied to the production system. It could be a form layer, or it could be a CNC machine that cuts the reinforcement, or it could be an ERP system that does the procurement for you. And the process is a very very easy process. Like you see three images over here. There's the one which has a model on the computer. Then the information from that model is extracted in the form of a PXML or Unitechnique file that kind of goes to the form that you can see on the assembly line over there. And there's just you just need to validate that the what the robot has placed as a QC stuff, so that you ensure that there's nothing wrong in this thing. That's why you need to have a drawing as well, for a person to read the drawing, and then you have the data that runs the robots and everything in the backend. So you can see there's this person just validating the stuff that the robot has placed. So this is a very easy stuff, easy process. Like, just get the model, get the architect's model, the other consultants, the engineers model, and everything. Just align it, see everything is producible, uh, break them into producible and transportable units, generate the drawing, PXMLs or the data files, and the drawings, the unit drawings, and then ship them to the factory to be able to produce those. So all this looks good and easy, but as coordinating on the project, we at some point of time we all would have experienced this kind of a confidence graph. Like this is called the Dunning-Kruger effect, and even I have experienced this a lot many times, like for almost all the projects. So what happens is you start building the project for approval. Like you have the input that you have, maybe the architect's model, the consultant's model, and all those input. You start building the model, and you are very confident. Like there's very little difficulties that you find in the model, and yeah, you're able to get that done. You have a very high confidence in the entire project. And yeah, your models do get approved as well, and that's a very um, peak of your confidence and your emotional state, and your team is also doing good. But yeah, you have a green signal, and then you start uh, detailing that model in a very production specific, or maybe with a very detailed view. Like you actually look into all the elements on a detailed level, and then you find some kind of things that might not be able to produce, or might need some kind of modifications, or they involve some changes or something that should be done. So there's where you kind of start feeling like, okay, this is not as easy it was, so you need to change some things. And then there's always some kind of design changes that happen on projects. Like it's I have never had a project that's like just has started and it ended without any changes, or maybe without any iterations of some kind. So yeah, there's these changes as well that are to be done on the model. Then there's whenever the design team, maybe the architect, the consultant changes something, then there's some other design changes that are to be done for the product, for the precast element. Maybe your connections might not fit in properly, so you might need to design that element in a different way, maybe align those joints at a different location or something of that kind. So it's like a lot of rework that's done at the model, like a lot of changes. The model was a lot more detailed now. It has a lot of information into it, and it has a lot of like it has gone through a lot of iterations to see what fits the production schedule and the production efficiency purposes. So this is probably like you are kind of at a low confidence with the project. And yeah, this won't surprise you. Like uh, you get the model approved and you find all the connections and everything to be very much working in the model. But when you extract the data out of the system, from the BIM model to from your model BIM model to the production machinery, you just get a lot of errors or maybe some kind of problems. Like the CNC won't cut the way you wanted it to bend or cut the bars, or the form would just not place the cuts, or maybe it won't procure the right stuff, maybe because of those things. And it is at that point you realize, like the changes, the architectural or the engineering changes that have occurred, this had a problem, but the consequences of those problems could be dealt with, like by looking at the model, or maybe by doing some clash checks or something. But you won't get the production issues sorted out unless you are actually checking that stuff. And if you do a root cause analysis of these issues, the production issues, I've generally seen it to be because of the interface that happens between the information exchange. Probably when you have an input from someone and you have to take the output to another machine. So what happens is you there's an interface that is created, and as I've said, like the strength of a system is equal to the strength of its weakest link, or the capacity of its weakest link. And generally these weakest links are the interfaces. And in an automated or semi-automated process, it's generally humans that kind of like take information from one end and take it and send it to the other ones. So this is where you find the weakest link in your entire BIM workflow. I mean, in case of precast, it is very evident. Like this is what happens. So when you call in a strategic meeting, you get all the lads around, like see if there's something you could do. Probably you kind of get into some kind of automation as well. You change the values, attributes, and all those things, and you get the model working to the production perspective. You start getting better results. Your machines are working well. They are following the input that you gave in, and you get better results. And then you have a lot of elements produced on site, like uh, those once the initial lot is gone out, you know the flow that needs to be followed, like what kind of attributes are to be followed, what kind of criteria are to be followed, what kind of uh, line types you need to keep in the model. So it is not like just making the model in a 3D space that is putting the information, but you have to generate data that is driving those systems. So you need to be able to communicate or talk with the machines. So these production issues that we have, this is probably the lowest point I've seen in the project. Like uh, you have a lot of data to be manipulated to get it right. But if you think about it, why do these production issues happen? So why do these happen? It's because not everyone thinks the same way. Like you would have a different method of modeling stuff, and the other person would have a different method of doing the same things. And the thing about precast is you have to generate a lot of data. Like every wall that is there has to have its own unit technique file, its own unit drawing, its own shipping or handling criteria document. So there's a lot of data to be generated, and it is sometimes it's not easy for a single person to do that. So you have a lot of people working on the same model, and a lot of people, when you're working with team, it sometimes happens that uh, the flow that you set is probably not followed by the other teammates. Probably they came up with some good solutions that help in saving time or increase the efficiency of the entire process, but it is like people think differently. So let me show you a couple of instances, like what happens and how things turned out differently. So let's just talk about a few cases. The issues that I'm going to talk about are not the structural or the engineering stuff, but the issues that came out of like BIM poor modeling or maybe different modeling practices that have been adopted. So let's just talk about thinking out of the box. I appreciate the team members to be able to thinking out of the box, but thinking out of the system is another thing. So when you are into a model-based generation or semi-automatic process, you have to keep everything consistent, like the way you model that, or the way you make modifications to objects. So this is a very important. This is an instance which happened. Like we had to change the wall heights for some reason. Like the wall was to be extended, and the way it was done was the person, he kind of just opened the drawing in CAD and he pulled those bars. I mean, like pulled the geometric lines, and he pulled those bars as well and updated the table and everything, and made it look very much generated from the system. So if you look at the drawing, you'll be like, okay, this looks good. It's legible. It could be produced easily. For a human person, it it is very much easy to look at the drawing, do the procurement, and produce it. But if you're looking at the system in a, I mean, like in a semi-automatic way, you need the data files to match with the drawing or the form drawings. So this is what happened. Like at this drawing and this file was submitted to the production line, and the robot did an assembly, and the assembly was not matching with the things that were on the drawing, and that's when the production the team kind of like saw, and they kind of came back as to like why is there a discrepancy. So it was a very creative way to save time and effort. But yeah, it's like you're not talking with a human, you're talking with the machine. You need to be able to know that as to what your actions are doing, what your actions are influencing on the end result. So this is one of the thing. Then this is another one, just to mirror it. So if you think about it, like most of the modelers that we have, they kind of still, like if they have a CAD background, they kind of still follow the CAD stuff that they do, like mirroring things up or maybe copying stuff and just stretching things, like exploding blocks or maybe something of that kind, like all sort of things that are done in CAD. But the thing is, in CAD there was human person, like an actual person who would read the drawings and procure and maybe work on the drawing. But in this system, it is an automatic, or maybe a semi-automatic, or maybe an automation in development. So what happens is, if you kind of mirror objects over, like there's three bearing pads that I've shown with studs in them, like long rebars welded to the plate. So the thing was, these were put in beams. So the parent is on the right side. The one in the orange is the one that was modified for grout tubes or something that were clashing with it, and the one on the left is mirrored over. So suppose I had five beams, and on one side I had the the one with the orange, and on the other side I had the one with the blue. So ideally what should have been done is, there should have been, if you could mirror the geometry, there's no problem with it, but the thing is, you need to know how the ERP system works. So it is essentially important, like the team knows as to what their actions are going to influence. Like in this case, you would just mirror it up and look, do a clash check and all those stuff, and see like, okay, this looks very good. But what happened on the site, on the production line, was this procurement that happened. uh, the name of this, like this bearing pad, was LXL, because it had a higher density on the L, and the left one, it had a higher density on the right. So what happened is, though this fixture was modeled in the mirror form, but its attributes or information was not changed. So the ERP procurement that happened, like for the entire level, that the ordering that occurred, it basically took everything from the orange one. It didn't consider that the there's some other fixture that needs to be placed in instead of the other one. So the good thing was that it wasn't actually ordered. Someone saw those numbers, and it was alarming. So it is important, like, how the changes in the geometry occur, or maybe what kind of information handling you're using. Like if there's smart attributes, like they automatically update based on the position of the objects in within the fixture. If it is smart enough, it can do that. Otherwise, you need to be able to update those, and you need to be very much vigilant, like as to change those attributes manually once you've seen it. So another thing is the weights. So in precast, weight is a very important factor, as to because you need to produce that element. You need to lift it from the form and place it in the yard, and then from the yard you need to place it on a truck, and then from a truck you need to place it into the on the site. So there's craneage involved in that, like, and this craneage has some capacity of its own, and it has some kind of cost involved as well. And so that's the reason you need to be very efficient with the weights. And getting weights out of a model is probably done in three forms. Like it could be density, it could be weight per object, it could be weight per meter. So the thing that happens is, sometimes you have objects modeled into the space, into the on the part or something. So these objects have some weight assigned to them, probably like sometimes we just don't model the windows. We would put some dummy fixtures into the part, so that it takes the weight of the window or something of that kind. So sometimes you have weight per object, like that's what the dummy window is. Or sometimes you would have the length per meter. In case of lattice girders or something, you would input the weight in the length per meter as to, because you won't want it to be calculating, or you don't uh, calculate the exact weight of the entire truss and everything. You just have a standardized weight per meter length, like. So you have the tables that generate the densities and weights accordingly. So you need to be very much uh, correct with the weights, or have at least have a factor of safety with the weights, because if the weights are incorrect, or they are low, that as compared to what the actual weight is, and it might cause some serious disaster on the site. Like if the crane fails or something, and the element is very heavy, and it's in the up in the air or something, it might cause a lot of problems. So density and weight is something to look out. The thing is, like, at higher, like I've experienced, like the weight was once higher, but the lift that takes the object out of the form, even it does the way that. So there are means to arrest such kind of disasters on site, but it is always better to reduce the errors or non-value adds at the start itself. Like, so these are a few problems, but what are the solutions to this? I would say just probably talk about things like what is the end philosophy of your process, like how why are you modeling the things that are you modeling, like why are you supposed to be doing this in a way. There could be better ways that come out, like that allow you to save a lot of time or maybe increase efficiency or improve the quality of your product, or maybe sometimes reduce the time spent on each and every deliverable. Like for an instance, you would have a drawing that is just used for validation purposes, that is not used for all the procurement and all those things. So you would be able to like reduce the time spent on that drawing for all the annotations that are done, like just make it fit for the purpose, like fit for the quality it is required, like just for the people to look at it, look at the what the robot has procured and make it, like instead of spending a lot of time on those drawings, like each and individual units, you could end up, you need to know what you need, and what how your actions are going to affect another. And the one of the most important thing is like humans are a very creative species, like they are able to be creative with their own work that they do. And I've often seen modelers or maybe coordinators as well coming up with their own workflows that are really good, but sometimes these just don't align up with the end process. So you need to be able to communicate or talk with other people. Just probably just sending an email as to what process you are changing could be very useful, like at least the other person would be aware of, yeah, this has been changed or something, or probably having a discussion would help. So communication is the key. We are able to be at the position we are because we've been able to communicate and work in a group. Humans have a very good ability to be to follow leadership, to work in a group. So yeah, communication is the key. And going a step further is to create validation systems. So this is like you could set up a ritual, or probably you could set up systems in your work that could help you to reduce or minimize the waste or minimize the problems that come out of sight. Like you could create just reviewing the model as it is being built up in the initial phase, like when it's just being built up, and telling the people who are actually working on the model, like okay, this doesn't works. Or maybe doing sample productions is very useful, like instead of having the entire flow being done, you could just produce some sample elements and see if that works, or what changes you need to make in your modeling method, or maybe tweak up how your apis or how your stuff works in that. And creating ways for people to find the information, like or maybe get in touch with the who's managing the project, like that's very essential, like having a teams channel or wiki page that like what all our attributes you need, and what is the flow of your project, like if in case this the you're trying to model this element, what is the end object, like how is it being produced, what is being used to procure those embeds, reinforcement and all those stuff, and at the last how is it being placed on site. Probably just giving a training on this to your team before you start a project would be very helpful, like if you can do that. And there's another thing, creating some algorithms that kind of check your units as you are working on those, or maybe generating unit drawings, or maybe some files that are there. So this is very helpful, like if you can get algorithms to check your models independently of the model. So this is the thing I like about maybe generating model and then generating a drawing, like in you could create algorithms that kind of just basically checking is just looking at things and comparing if this one matches or not. So algorithms are better at this as compared to humans. So it's very useful if you could like automate some process of this validation system. At least it could flag in something. I'll talk more about this. So this is the philosophy, like if in doubt please ask. So The way these, what we do is on our drawings, like these are a bit independent from the model. So if you're trying to generate a drawing, this will try to look up for values in the drawing, in the model, and it will compare with a database of the accepted uh, attributes or accepted values. Like in case of lifting, so suppose there is a wall and you have the capacity of each lifters, it will check the model itself, like this is the weight, because the weight is in the model. This is the capacity of the lifter, because the lifter is also in the model. And it will compare how many lifters will it need, and if the count is matching, it'll show the drawing correctly. Otherwise it'll try and fill some kind of stuff, like it'll just put some stars or something of that kind, just to flag it, like this doesn't seems to be correct, and it needs some human intervention into it. Like you just need someone to go into it and check as to if that's correct or not. And yeah, about that, fixtures, and if stuff is mirrored up or something, you could also get that in the form of a table or something on the drawing. That kind of, just when you generate a drawing, it'll try to look up for those values, and it'll flag up things that are not correct. So even if the person who's doing QC in your office misses out, the people on site, I mean, like on the production line, would see something that is probably not legible, probably has some kind of exclamation marks or something, and they could inquire up, so that you end up arresting those errors. So this is one of the ways we've been working with it, and it's been proven to be very helpful to us. And with this, I've and this is the end of my presentation. I would invite you to have questions, if any. I'd be glad to answer those questions.